It smells like the food.
That's rare.
They take pictures.
Yeah.
That they go to like everywhere.
There's a difference. That's all bad.
I know.
In a church, that's like religious spoiled, whatever.
It smells bad. One time they went on this right side. We probably have
Are we not using it? It doesn't work. It barely charges up. And I spent, I don't know, 20 minutes working on it, and I just don't have the time to invest in looking at it anymore. So chapter 21, I think, is called the electric field or something like that. And the first thing I think of when I hear the word field in reference to physics is like force field. And that's a good word to associate with our electric field. So our concept of an electric field, what do I want to use for this? Let's pick on the balloon. Let's pick on the balloon. The balloon is good at getting which type of charge on it? Are balloons good at taking electrons or giving electrons? Yeah, balloons are actually pretty good at taking electrons, so when I rub this against a lot of things, including my hair, including wool, whatever, the balloon contains a negative charge. And then we already know that the balloon can push and pull on other things in the space around it. And yes or no, it's able to push or pull on things that it's not touching. That's a great question too. Does the balloon have to touch things that it's pushing or pulling on? No, it does not, right? No, it does not. And I can probably prove that by if I'm able to pick up any punchies with the, well, if I'm able to pull up any punchies without touching them, then that would be pretty good evidence. And I did, right? I got a few punchies to fly up and stick onto the balloon. So the balloon was able to reach through empty space and pull on those punchies, right? So that force that the balloon is exerting, if we think back to like October, we would have classified that as a field force, right? We have contact forces and field forces, and the only field forces we said that are kind of within our experience were gravity and electricity and magnetism. So we've actually already used the word field before, but we never really looked too into it besides just saying that we call forces field forces if they don't need direct contact. Alright, so the balloon is able to pull on things without touching them, and that is because the balloon is physically changing the space around it. Right? Even without any punchies present, the balloon is trying to pull on stuff that's surrounding it. Alright, I just got a dirty look, so let me pause. Problems with anybody saying that the balloon is physically changing the space around it, and that's how it's able to push and pull on things that it's not touching. Okay, well, if you are fairly happy with that statement, then I don't think you should find the concept of the field very disturbing. Alright, so let me catch up with the notes here. So a charged body, just like a massive body does this with gravity, a charged body changes the space around it by virtue of having a net electric charge. So there is literally a force field surrounding this object, and the force field is able to exert that push or pull on other charged things. Right? So our name of the our name field is really just a term to describe this effect that our charged object is having on the space around it. Right? So a field of force exerts a force field. So gravity does this, electricity does this, magnets do this as well. So we're not going to spend ridiculously long on this concept or on quantifying electric fields, but it is of some importance. So I do want to devote probably just the rest of today, or most of the rest of today, on both quantifying the strength of this effect on space, quantifying the electric field, and then drawing or depicting the electric field around things also. And if we want to test the electric field around a charged object, we really need to put something in it and then gather some data on what happens to that something. And a punchy is not an ideal thing to test the field with. We actually would want a charged thing to test the field with. So we call whatever we're going to test the field with, we call it a test charge, because we're using a charged thing to test the field. And a test charge really needs to just meet two criteria. It needs to have a small amount of charge, and it needs to be positively charged. There's no good reason that it needs to be positively charged, other than when we do it, we want to agree with other people that are doing it too. So it wouldn't work very well if we were using negative charges to test fields, and like in Australia they were using positive charges to test electric fields. It wouldn't really work out. So just like the whole international community has agreed, we're always going to test fields with positively charged things. So there's no great reason that we're doing positive. We just want to all use the same thing, and flip of a coin, we pick positive. I'd like in your foursomes for you to see if you can come up with a good reason why our test charge should only have a very small amount of charge on it. Alright? So talk in your foursomes, see if you can come up with a compelling reason why we want a small Alright, actually I think all the groups responded. Alright, so Hannah, what was a compelling reason that you guys thought of?
We thought that it needed to be able to have charge so we could track.
Okay.
But not big enough so it had an effect. So
Yeah, so if we have two large amounts of charge, then we can't very effectively test the field due to just one of them. If we have two big charges, they're both producing electric fields. And what's dictating the behavior of the system? It would be both of them combined. If we just use a very small amount of charge, now I don't mean a physically small object, I mean a small amount of charge. If we just have a very small amount of charge in this balloon's field, then the entire effect, or 99.99999% of the effect, would be due to the field from the thing with more charge. Right? The thing with a small charge would have a very small field, so it shouldn't be influencing the results very well. All right? So a strong field, so actually this is a separate thing. So our test charge needs to be positive, it needs to have a very small amount of charge. It probably should be small in size also, but just so that we're testing the field at a very precise location. A strong electric field is going to pull on our test charge with a small force. A weak electric field should certainly pull on our test charge with a very small force. So who is an ideal test charge? Who would be the perfect test charge? Who would win the test charge election? Just the Owens. Nope. He's alive. A what? A proton, right? Would be perfect because it's positive and it's the smallest unit of charge that we can deal with, right? So a proton would win the election every day of the week to be a test charge. Alright, so I want to do some sketches first, some simpler sketches, then we'll move on to quantifying the electric field, then we'll come back and do some slightly more complicated sketches. We're not going to do any ultra complicated ones. So let's see, let's do our balloon. Alright, here's our balloon, there's a little nozzle where we tied it off, and our balloon was charged how? Our balloon is charged negatively, right? I would actually recommend that you don't sketch this yet. Alright, so let's put a proton right here. Show me with your fingers which direction that proton is going to be forced by the balloon. I'm getting most of you pointing this way, which is correct, because our proton is positively charged and it would be attracted to our negatively charged balloon. What if I put a proton all the way down here? Show me with your fingers. Yeah, up, but it's actually going to be it's going to be a much smaller force than this one was, right? So our distance from our charged object is going to influence the force, obviously, because Coulomb's law tells us that. Right? And we could use Coulomb's law for this. If we used it here, QA would be like the balloon, QB would be the proton, and then here would be the distance. We'd have the same QA and QB here, but our distance is much larger. So we would have a weaker force further away. But we could do this all day long. Wherever we put the proton, it's going to be forced towards the balloon. And if we're always using positive test charges to map our electric field, then we should end up with a field that points in towards our source of the field, no matter which direction we're coming from. So this one I do want you to sketch. This would be the good, cleaner version of an electric field. So we have a negative charge creating the field, and then we're going to draw field lines that just come in and point in towards that negative charge. I'm going to do 8 field lines. Oops, that one's wrong. I think we should do a minimum of 6. I don't think 4 is quite enough. And I'm trying to be neat about it. I'm trying to be symmetric. I'm trying to get the arrows to end right at the surface of the negative charge. But this would be our first example of an electric field diagram. And we would call these arrows field lines. So anywhere along that line, the field point, well, the line shows us what direction the field goes. Questions about sketching that? I do have something else I want to comment about it before we do another one, but questions about this method of depicting the electric field due to this negative charge. Please recognize that this is a 3-dimensional thing, so we would have a field portraying out of the board, which would point in towards the negative charge, but I really can't draw that in 3 dimensions. All right, before we move on to quantifying, let's do the same thing, but for a positively charged region of space. All right, so this time we have a positive thing that's producing an electric field. We're going to have a similar looking field, but the field lines will point outwards, right? Because our test charge is still positive, and this time our test charge would always be repelled away from the source of the field.
So our field lines always perpendicular to their outline.
Are they perpendicular to their... the field lines always leave the charged object, yes, perpendicular to its surface. That is correct. Yeah, that's not always. That's a rule. They can curve. We're going to look at those later. Yeah, Jane.
Will we use these like lines for problems, or are these just like
We would, you might need to draw these to help you find the direction of a field for a more complicated problem, but more likely I would say, hey, show what the electric field looks like around a single negative charge. For more complicated problems, it does come in handy to help us establish the direction. Alright, now the other thing I want to point out before we move on to quantifying the strength of the field is I want you to notice that the field lines are closer together when we're closer to the source of the field, and then further apart, right? It's a greater distance between field lines as we move further away from our charge. And sometimes we call that the field line density. We kind of represent the spacing between field lines. That is related to the strength of the field. So the closer together the field lines are, the stronger the field is. The further apart the lines are, the weaker the field is. But we already knew that. And we already knew that because Coulomb's law tells us that the force is weaker as we move further away, and the field is very much related to the force. Okay, so the density of the field lines does give us some kind of semi-quantitative information about the strength of the field. Alright, enough of drawing right now. We'll come back to drawing in a little bit. We have used most of the letters of the English alphabet and a lot of the letters of the Greek alphabet. So we do start having some repeats at the end of the course. Our symbol for electric field strength is a capital E. Right, a little bit confusing because we've already used that for energy, but oh well, I think we'll be all right. And the strength of an electric field is defined as the force acting on a test charge divided by the amount of charge on the test charge. So you might notice that this Q has like an apostrophe after it. The apostrophe is indicating that that's the test charge's charge, not the charge creating the field's charge. Alright? So if we're going to drop our proton here, the electric field strength would be the ratio of what is the electrostatic force exerted by this guy divided by the charge of the proton. Right? And the force is what we would get from Coulomb's law. Alright, so it's the force acting on the test charge divided by the charge on the test charge. The unit for electric field strength is just the unit of force divided by the unit of charge. So it's just newtons per coulomb. We don't have any like fancy like new unit that we abbreviate that for. And then again, just like I said, the F is the force that the test charge is feeling. And then the Q with the prime is the amount of charge on the test charge. So our electric field strength is force per unit charge. Alright, so let's go ahead and quantify an electric field. We'll probably do a couple more, and then we'll go back to drawing if we have time. So let's check out our first example of this. We have a positive test charge, it better be positive, of 2.2, what's the P? Pico or pico, right? And I think that's short for, I think pico is 10 to the negative 12. Does that sound right or wrong to anybody? No? Well, if somebody could kind of check that out. I think it's on the back cover, like the inside back cover of your book. That would be helpful. So we have our very small amount of charge, right? 10 to the negative 12 is a tiny prefix. It's in an electric field that's pushing or pulling on it to the right with a strength of 3.2 times 10 to the negative 5 newtons. We want to find the magnitude of the field, so the field strength, and we want to find the direction of the field as well. Right? Did anybody find it, the pico? It's not there? Then it is 10 to the negative 12? Oh, it's not. How is it not there? Is it 10 to the negative 12? Let's see. Oh yeah, no, it's back there somewhere. Maybe it's in the front somewhere. It's in chapter 1 somewhere. Pretty darn sure it is 10 to the negative 12. Yeah, page 6, pico is 10 to the negative 12. Yeah. All right, so we are supposed to sketch something, and I actually am not sure what to sketch because I don't know what's creating the field. I don't know if it's a positive charge or a negative charge. So what can I do? Yeah, I don't know. I guess I can draw the test charge and at least show that it has a force acting on it to the right. That's useful information to sketch out ahead of time. The 2.2 picocoulombs is the amount of charge on the test charge. So that's Q prime, or it's Q with the apostrophe. And then I'm going to go ahead and change that into regular coulombs also. So 2.2 times 10 to the negative 12 coulombs. We know that the force acting on it is 3.2 times 10 to the negative 5th newtons, and that points to the right. And we want to find the electric field, both the strength and the direction. All right, questions from anybody on my attempt to draw a diagram that would help, and my step 2 and my step 3. Alright, well step 4 we only have one equation, at least so far, for electric field strength. It's the force per unit charge on the test charge, so that's pretty straightforward. 3.2 times 10 to the negative 5th divided by 2.2 times 10 to the negative 12th. That's going to end up being a kind of big field strength, or at least a large value. Alright, so I'm getting something like two significant digits, so I'll call it 1.5 times 10 to the, what is that, 7? Right? What is that, you got 7? Oh, no. Make sure you put these in parentheses, you shouldn't get 17. 7? Anybody else with 7? Only like 3 of you are doing this? Alright, let's go to see, I'm pretty sure it's 10 to the 7. 1.5 times 10 to the 7th newtons per coulomb. That's half the solution. Questions from anybody on arriving at that for the strength of the field? That's huge, right? So 1 coulomb of charge would have 15 million newtons of force acting on it. It's pretty big. And then we need the direction also. So let's see, I think I have 2 possibilities, at least 2 easier possibilities for what is producing this field. I could have a positive charge producing the field, or I could have a negatively charged region of space producing the field. And the positive charge would have a field that points outward, and the negative charge would have a field that points inward. Now, what we know is that our test charge is positive, and it's getting forced to the right. So I want to place the test charge in this field where it would get forced to the right. And where would that be? Top right, bottom, or left? It would have to be on the right. The only place that the positive test charge would get forced to the right would be on the right, because it's repelled by this thing. So here's one possibility is that the field points to the right. Okay? Let's look at where we would have to place the positive test charge over here to get it to be forced to the right. Top right, bottom, or left? Left. Okay? If I place the positive test charge here, the negative charge would be pulling it to the right. And that also has an electric field that points to the right. So regardless of whether we have a positively charged region of space or a negatively charged region of space, the field that's making this test charge be forced to the right points to the right. So the electric field is 1.5 times 10 to the 7th newtons per coulomb to the right. I actually don't need to know who is producing the field. So Jane, that's why sometimes it helps to do the diagram in association with a quantitative problem. All right, so let's get you guys trying one of these on your own. If you have questions about that one, it'll make more sense if you're applying it in a new situation. So I want you guys to try this one, right? We have, okay. What is the magnitude of the electric field strength at a distance of 87 centimeters from a point charge of negative 8.4 microcoulombs? I lied. I don't want you to do this one on your own because it's harder than the last one. So let me do this one, and then you will have seen, standard ones and harder ones. We haven't seen point charge before. Do you think that means the same thing as test charge? Probably not, because if I meant test charge, I'd probably say test charge. All that a point charge means is that this negative 8.4 microcoulomb charge is small. We're treating it as a point in space, not like a big fat thing like a balloon. Alright, so a point charge just means that all of the mass of it, all of the charge of it, is at a single point in space. So this is the thing creating the field. Right? This is the thing creating the field. If you didn't take notes on the last one because you knew it was going to be easy, I highly recommend that you do take notes on this one. It's not as easy. Alright, so I'm going to start off with step 1. And this time, I absolutely know who's creating the field. It's this negative 8.4 microcoulomb point charge. So for step 1, I am going to sketch the field pattern surrounding that. So there's my step 1. Step 2 is to identify the information that we know. So we want to find the field strength, not the direction, 87 centimeters away from the source of the field. Wow. Alright, so 87 centimeters. I know I need to change that into meters, so 0.87 meters. I am going to call that R, and you'll see momentarily why I'm choosing to call it R and not like D or delta D or whatever. And then we know the amount of charge that's creating the field. Is that Q with the apostrophe? No, it's not, right? That is our charge that's creating the field. I'm going to do a capital Q for that because it has to be a big charge. No, I won't do a capital Q. That's confusing. I'll just do a Q without an apostrophe. And that's negative 8.4 microcoulombs. Micro is 10 to the negative 6. So negative 8.4 times 10 to the negative 6 coulombs. And I'm looking for the field strength. I'm not going to pause for questions just now. I only know one equation that has electric field strength in it. And I cannot use that equation, right? Because I don't know the force, and I don't know the amount of charge on the test charge, right? So who knows what I'm going to do? Who actually looked at these examples in the book? Henry, what am I going to do? I need to incorporate Coulomb's law into this solution. This force is our Coulomb force. Okay? So I need to put this in for my F. Alright, so K, instead of QA, I'm just going to do Q, which is what I call the thing creating the field. Instead of QB, I'm going to do my test charge, the thing that I'd be testing the field with. I need my R squared, and then I still have the test charge in the denominator. And algebra says that I'm allowed to cancel out the Q prime, because it's in the numerator of my numerator, and it's in my denominator as well. And then I'm left with an expression that has the Coulomb constant in it, it has the charge that's producing the field in it, and it has the distance squared, the distance of how far away I want to know the field strength, how far away I'd be placing the test charge. So we actually can calculate the field strength without any knowledge of the test charge, right? And that is something that I would expect you to be able to do on quizzes, mega quiz, final exam, whatever. All right, so let's finish that one up. So I'm going to actually move to the left. So 9.0 times 10 to the 9th is our Coulomb constant. I'm not going to care about the negative sign on my charge. I'm just going to put in 8.4 times 10 to the negative 6. And then I have to make sure that I square my distance, right? Just like the force, the field is inversely proportional to the distance squared. And I get a smaller field than the previous problem, but it's still pretty big. Another one that rounds to an unfortunate thing. So I need to round this to 2 significant digits. Everything rounds up. So 100,000, but I have to make the thousands place significant. So this would be 1.00 times 10 to the 5th newtons per coulomb. 100,000 newtons per coulomb. Pretty much as hard as stuff you get. We just have to remember that the force in our electric field expression is our electrostatic force from Coulomb's law. All right, so now I hope we're ready to do some more on our own. I do have that derivation in the notes, right? So we're just substituting in Coulomb's law for our force. Here in the notes, I actually did more Coulomb's law so that QB was just the test charge, and I did use a capital Q in the notes. We often do that because the thing creating the field should have way more charge than the test charge. I don't remember what Mr. Schultzowitz does there. All right, I don't want to try and squeeze electric potential energy into today, so let me get you guys trying one easier one and one harder one in your foursomes, and it'll probably be time to go to lunch at that point. So what I'd like us to do is chapter 21, number 1 and number 6. All right, I will put Mr. Zintowitz's answers on the board. please call me over if you guys get stuck or if you disagree about something.